So information is spread throughout this video, so please see the description down below for the timestamps. There is also a small montage before the 3D CAD section of some of the bikes that we saw at the motorcycle show. I'd also really appreciate any feedback, good or bad, on the formatting of this video. Please let me know in the comment section down below. If you have ever tried to upgrade your exhaust system and ended up with worse performance and you've not understood why, well, hopefully with this video will help you understand, and maybe you'll even be able to design your own system. We're going to start with taking a look at the intake, combustion and exhaust system. This is important to understand the key design points for the exhaust system. From there we're going to move on to the 3D modeling of the exhaust systems, at least as far as we can go without modeling the internals of the muffler or the catalytic converter. Then at the end of the video we'll have a deeper dive into the engineering design. Now I'm assuming everyone understands the concept of a 4-stroke engine, but we're going to summarize it now with this cut section. Now for any internal combustion engine to work, we need 4 main things: fuel, air, spark and compression. So air and fuel is first pulled through the intake valve into the cylinder. It's then discharged via the exhaust pipe via the exhaust valve. The valve opening timing is controlled by the camshafts and the camshaft's relationship to the crankshaft. The camshaft rotates at half the speed of the crankshaft and is assembled in a way to ensure that the valve opening is in the perfect timing relative to the pistons, which are mounted to and governed by the crankshaft. So the crankshaft, camshaft and cam chain ensures the relationship between the piston movement and the valve opening, hence why timing and chain tension is important. And lastly, for gasoline engines, spark plugs. Now taking a look at the camshaft lobes, they have this egg-like profile. This profile defines the speed at which the valve will open. It's roughly 110 to 115 degrees around the lobe, which means the valves will be open for 220 to 230 degrees of crankshaft rotation. For a 4-stroke engine, the crankshaft must rotate 2 times, that's 2 strokes per rotation. Let's consider the simplified engine model. Our volume is on the x-axis and the pressure is on the y-axis. A downward stroke would increase our volume and an upward stroke would decrease our volume. Let's consider each horizontal as a stroke. So number 1 is the intake stroke, number 2 is our compression stroke, number 3 is our expansion stroke, and number 4 is the exhaust stroke. The sudden jump in pressure on the far left is due to combustion, and the sudden drop in pressure on the far right is due to the release of pressure when the exhaust valve opens. So the intake valve is only open during the intake stroke, and the exhaust valve is only open during the exhaust stroke. Each valve then is only open for 15 to 20% of a cycle. So the cams aren't acting directly on the valves, they are actually acting on the buckets or followers which hide the tappets, the valve retainer and the spring. So for an engine idling at 1400 RPM, the exhaust valve is going to open roughly 12 times per second at 13.7 milliseconds. When cruising at 6000 RPM, we'll be opening around 50 times per second, that's 3 milliseconds, and then at 14,000 RPM, we'll be opening about 117 times per second, down at 1 millisecond. So from this we can understand that throughout the RPM range we're going to have very different conditions in the exhaust pipe. It's going to be near impossible to design for all conditions, so we need to choose where we want to prioritize. Essentially what we have here is the number of pulses that's going to occur every second as a result of the exhaust valve opening and the exhaust stroke. And this is where exhaust tuning comes in. Ideally we want to pull as much exhaust fumes from the cylinder, dropping the pressure to increase the differential pressure from the intake into the cylinder, allowing more fresh air and fuel to come in during the next cycle. We call this scavenging or pulse tuning. Now we're going to need to talk about fluid dynamics. Now for any flow to occur, we require a positive pressure differential from upstream to downstream. As the fluid flows downstream, we're going to have an amount of friction loss. Essentially, we are losing pressure as a result of friction. Now if this friction loss is so high that we have no pressure differential, then we will have no flow. So one key factor that influences friction loss is velocity. Usually if we have a fluid flowing down a pipe, we need to send a certain flow rate. Now if you have the same medium and you want to send the same volumetric flow down two different pipes, one larger and one smaller, it must travel down the smaller pipe at a higher velocity. Meaning that by using a smaller pipe, we're going to create excessive friction loss, which results in back pressure. On the flip side, however, if you have a larger diameter, we're not going to get a high enough velocity to encourage the effects that we want in the exhaust to aid in the scavenging. We'll also end up with a larger, heavier pipe. So what kind of effect do we actually want in our exhaust system? When the exhaust gases are flowing down the pipe, they're flowing extremely fast, just for short bursts because of the pulsing action of the valve opening and closing. What this results in is, as it reaches an expansion in the diameter of that pipe, we'll have a pressure drop. And that pressure drop is going to pulse back to the exhaust valve, helping to pull out any remaining fumes and even potentially pulling it into a vacuum condition. Ideally, we're aiming for a greater differential pressure between the inlet and the chamber. So pulse tuning is all about sizing the diameter and the length of the primary pipe, or depending on the engine, the secondary pipe as well, in order for the pulses to arrive back at the exhaust valve at the ideal time. This is not going to be the same throughout the whole RPM range, hence why we have to select where we want it to be tuned for. Okay, so we'll revisit this again at the end, but let's for now get onto some 3D modeling. Okay, so I'll start with just clarifying that I was part of the chassis design team, and typically not so involved with exhaust systems. I have studied how to design them in regards to length and diameter in the past for things like pulse tuning, but never actually put this into application. So this was quite a fun exercise to revisit those kind of engineering calculations, and then also quite fun to try modeling an exhaust system which I've not done before. In this video I'm only going as far as, say, where we may have a catalytic converter, but in this case, since we're not necessarily trying to make something like production, you could just have fun and try to model some interesting NCAN here. Maybe we'll do that at the end. So I've already spent a little bit of time figuring out how to best model the pipes and how to join them up, whether to use servicing or modeling. So I'd just like to share what I found using Fusion 360 to model some exhaust pipes. First off, it would be useful if before you start, you use some visual reference for your ground clearance. I obviously didn't do that, and I also probably could have used this for reference for sizing the pipe diameter. I have oversized the downpipes on this model. And also another factor is your bodywork. You should probably do that before, you should probably do your bodywork after you've designed your exhaust system so that you can have enough packaging space, because packaging space is one of the worst issues, one of the biggest problems for things like exhaust systems. Let's just leave the engine block. Actually, no, let's leave the chassis in there so you can get an idea of how much clearance we have. We do not have enough. This is not yet good enough. So I had my roughly modeled engine block, and I modeled a few cylinder exhaust ports. Now we'll just break down the exhaust system model. So the first thing I did was to create the components that make up the assembly. So importantly, we have a collector, and then we got the 3 downpipes. In this case, you may have 4 downpipes or 2 for a twin or something, maybe even 1 if you're going for a single cylinder. Ultimately, what we did here is I wanted to start with the collector. The reason for that is because I knew that I wanted to route the pipes from here to wherever I specify the end of the pipes on the collector side. It's much easier to model from a fixed point to the point that's likely to move, instead of trying to get a random point and then bring that to a fixed point, at least in my experience, or in my opinion. So So how do we model this? So we bring this to the collector. The collector started off as a simple sketch. Let's bring the sketches in. We roughly positioned the datum, and then I specify a sketch. So this sketch, the diameter of the collector should be larger than any single downpipe, but it doesn't have to be the same cross-sectional area as all three combined, because they're not all going to be discharging at the same time. We're not going to worry about choking the flow. I was considering modeling this in surfacing, and I did have a little attempt, but I found that there were some issues. Trying to bring those surfaces together and fill in certain rounds. So something that I would have to practice with a bit more to really make something worth sharing. But what I did find was using solid modeling would be easier for joining these together. With our sketch, I extrude a section here, and then from there I know I want 3 pipes to connect to this one, so I offset to where I want those to be, and then I place a sketch for each of those 3 pipes. I wanted them, I guess if you draw a triangle, you triangulate it to find the center point. I wanted that to be coincident with the axis of this tube. So from there, what I knew I needed to do, or what I wanted to do, was to draw a sketch between each tube back to this this initial tube. In order to do that, what I did was to create an axis through the cylinder. So if we come into construction, we go axis through cylinder, and we place that axis there. After that, we create a plane through 2 edges, selecting this edge, the axis that we've created in this cylinder, and the z-axis. That gives us a plane that we can sketch on really easily between those 2 cylinders. It's I guess it's an alternative to doing 3D sketching, but we just have a bit more control of the planes. From that sketch, we then just sweep the profile back to the initial tube. You can see the initial tube is oversized currently. That's because I plan to extend and draft or taper the extended tube into these 3 tubes that are combining together. From there, we have another sketch. Basically, we're going to repeat this for each one. So we'll skip forward. Once we got it like this, it can be a bit difficult because you see these are all individual bodies, and to merge them together we need to do some funny stuff with combining, because it was having some issues clashing. So what I wanted to do here was extend the end here with a taper. So if you just extrude, select the undersurface, pull it out a distance, and then add a negative taper, that will reduce the diameter. Then I used the combine feature, which is up here. But when I use the combine here, I use the cut operation. So I'll use this body to cut the ends of each of these tubes. That makes it so that they can all just marry up to this this larger diameter tube. Problem is they all still clash with each other. So again, we've got a number of combined features here, which is all just selecting each of these bodies and getting them all to chop each other down until they're basically no longer intersecting, but they are just meeting up together. From there, we then merged it with the main block here as well, so you have a single block now. Okay, so we have this single single body. Now obviously it doesn't look so great. We got a lot of straight edges, so we wanted to get a round in here. This is where we have some problems. Getting this round in was a little bit tricky for some reason. If you try to put a round, if you select the round feature and you try to click in here, it's not going to like it. Let's show you what I mean. So this one, let's say 3 mil. That's no problem. Let's select here. Okay, that's no problem. And select there. Now we have a problem. So for some reason, if we select the top, maybe it's the angle at which we're looking at, it doesn't like it. So what I found was when I was placing my rounds, if I always select the bottom, I never had a problem. You get all 3 of them in, no problem. And I wanted to boost those up as large as possible, because we will be reducing the material thickness here, and that allows us to have slightly thicker walls. After getting that round in, we put the round around the larger pipe, the connection point. Then just finishing off the rounds, we use these shell features. So the shell feature you can use to make a block into a box. Just take away the walls, but you specify how much you want the material thickness to be. You can do the same thing with tubes like this. So in this case, the largest I can get it was about 1.8 millimeters because of the way the geometry is ended up. So that was the collector. How about all the other parts? So let's go to the middle. The middle would be the simplest, because obviously that one we just have a simple straight line. So in that case, what we did was we create a sketch on the center plane and bring that straight down. For this, we use just create references. When we're in the sketch, we can create references. And we create references for each of the tubes, just so that we make sure that we are connecting to those places. And later, if you want to move the collector around, as long as you did these sketches correctly, it should all still be intact. Okay, so from that sketch, we then need the profile that we're going to sweep. Then we sweep that profile, and then we merge that together. And then we come on to the next one, which looks to be the right-hand one. So for the right one, it's a little bit different. We start with using surfaces to offset the surfaces of the collector. This is just to have reference surfaces within our model, but we don't want to keep them live. We don't want to keep the link live. We want to kind of break that link, that reference between those two components. So if you right click on a component at the bottom, you can convert them to a DM feature, which essentially means it's no longer linked, and you just have a copy of the surfaces within the model. And then you can use those for reference for things like construction points and construction axes and things like that. So from here we follow a similar approach. We put these 3 points, and then we use surface on 3 points, so that I can do my first sketch for the part of the tube. Now, this part of tube it could be an angle. You can make this a bit more interesting, obviously, if you want to design the collector in a slightly more less straight shape. But just for the purpose of this video, we have a section of the pipe extruded out. I only go as far as here, because then you notice we have some angles that we have to work with. So the thing I did here was to put my axis here on this new tube that we've created, and then we have a sketch which I create on the main datum, but in this case we do go to 3D sketch. So within that sketch, on the sketch palette on the right here, we got the 3D sketch. And I've ticked that so that we can work in 3 dimensions. Since I started with this part, I create a reference to this, and then I first sketch out this line here. Then I come back up here and I sketch out this line. And once we've done that, it's much easier to just draw one straight line between each of these lines, because it will snap to each end. And once we've done that, we can then use the round feature to round our sketch geometry. From there, then we sweep the surface just like that. Now, of course, the mounting plates, I want to say the manifold, the plates that are going to be bolting to the engine to secure your downpipes, your headers, your exhaust. For this, I just made a similar profile to what I put on the engine. Do notice that the exhaust pipe does go inside the engine. It does extend within, say, like an inch or so. Yes, so that's about as far as we have for this. Some things to bear in mind. If you have a real model for your engine, or what you're modeling here, if you have a real reference, then you can check everything in regards to packaging. I can see very clearly that I have no space for a radiator in this case. As soon as you have any travel in that front wheel, we're destroying the radiator. This definitely needs to be pulled in, and then the pipes need to probably be pulled out and do some more twisty geometry. There are a few other important things. Obviously, we're going to have an oil filter here, which is always a culprit of draining oil all over your downpipes. Your various different things down here. Your horn as well is usually located down here. So for a production motorcycle, obviously they have to worry about regulations and emissions. So from this collector, we'd usually go directly, or maybe not so directly, but we will go into a catalytic converter. Within that, you've essentially got like a lattice shaped construction. All of the surface area on that material, once it gets hot, it's able to absorb and catch the emissions that we're trying to prevent being exhausted to the atmosphere. For a lot of production motorcycles nowadays, they often have the end can, or the outlet of the exhaust, just under here. And for me personally, I feel like that's a shame, because your exhaust is one of those things that it's like a style. It's like a part of the style, and if you're hiding it under the bike, then you're never really seeing it. So I've always like what I'm used to seeing on like older early 2000 motorcycles and mid 2000s. I like to have the end can up here, side of the swing arm. Now, if you look at a real motorcycle, what you're going to see here is a lot of twisting around of these pipes. The reason for that is they need to be roughly the same length, say roughly as close to the same length as possible, because each cylinder should be the same capacity. They're going to have a slightly different firing order, but the exhaust gases are going to be traveling down these pipes. And when that gets to the expansion, that's where we get the pulse. And we want to tune it so that each cylinder is as efficient as can be at your selected rev range. So usually what you're going to see is some long sweeping bends in the exhaust, and the reason for that is, one, packaging. It needs you to do that in order for it to fit, but the main point is actually for friction loss. So if you have a very sharp bend in your pipe, you can have a much greater friction loss than if you have a long sweeping bend. That long straight bend may be good for reducing friction loss, but that sharp bend is going to be worse in the long run. So I think I'll probably make this a two-part series, because I have a lot to talk about for both parts, whether it's the engineering side or the 3D modeling side. So yeah, we'll leave it there and we'll move on to the end can in a following video. Now, I don't usually do this, but let's take it to the whiteboard. So in order for us to have flow through a pipe, we must have a positive pressure differential, meaning that we should have a higher pressure here, for example 1 bar, to 0.5 bar, giving us half a bar differential pressure. Now this differential pressure is a result of many different things. One of those being the friction head loss as a result of the friction as the fluid flows through the pipe. So one key factor that influences the amount of friction head loss is the flow regime. Essentially this is how turbulent is the flow, or what's happening within the flow. So we start off first with laminar flow. This, you'll probably be familiar with the videos you see where a liquid looks like it's not flowing, but it actually is. This is laminar flow. It's extremely smooth, very low friction. Then we have transitional flow. So this is kind of in between the laminar flow and the more turbulent flow that we'll come to. So it's fairly smooth, but there's some turbulence here or there. This is your typical flow. Then we have turbulent flow. This is the worst case where we have excess friction. So in fluid dynamics, we have a unitless value, which is called the Reynolds number, which is used for calculating friction loss. We start with taking the density of the fluid, multiplied by the velocity, the diameter of the pipe, over the dynamic viscosity. And you can rearrange this if we take out the density, we flip it with the dynamic viscosity, we can get the kinematic viscosity, making a slightly different equation here. Depending on the value that we output from this, we can determine what kind of flow we have. So if it's below 2000, we have laminar flow. If it's between 2000 and 4000, we have transitional flow, and over 4000 is our turbulent flow. So why do we care about this? Essentially, this is our exhaust pipe. Any excessive back pressure that's created from the friction loss is going to be applied to the chamber, preventing the exhaust gases from discharging. So what's actually happening in our exhaust system? Since we actually have a reciprocating piston here, and we have this valve which is also opening every 2 rotations of the crankshaft, we have an intermittent discharge of exhaust gases. It's not continuous. This results in a kind of pulsing nature of the exhaust. As the exhaust flows down here, we're going to reach an expansion. When a flow of gas or fluid reaches an expansion, but we maintain the same volumetric flow, we're going to have a drop in pressure. That drop in pressure results in a kind of rebounding negative pressure. This is like a pulse, and it's going to pulse back to the exhaust valve. That negative pressure is essentially resulting in a positive differential pressure across here, a greater positive differential pressure, which helps to pull out more exhaust fumes, more exhaust gases. And this is the concept of pulse tuning. Okay, so this is a very simple approach, very simple theoretical approach, pulse tuning, sizing the length of the primaries. So firstly, we specify whether we're using four-stroke or two-stroke. That's going to tell us how many exhaust cycles we're going to have for every minute, for example, based on our RPMs. So assuming we're idle, 1400 RPM, something like that, we'll have an 700 exhaust cycles per minute. Depending on the cam valve design, this is the lobe that we spoke about earlier, the actual amount of degrees that the exhaust valve will be open may be something like 75 degrees by that cam. But since the cam rotates at half the speed of the crankshaft, if we look at how long the exhaust valve is open by crankshaft rotation, that should be double. So we got 150 degrees on the crank valve opening here, or the exhaust valve opening by crank. So the next thing I want to know is the time per degree of rotation. So to get that, we first calculate the revolutions per second. So we take the RPM, divide by 60. Then for the time per degree of rotation, we take 1 second, we divide that by 360 degrees times by the amount of revolutions in that revolutions per second. So then so the next thing I want to know is the time per degree of rotation of the crankshaft. For that, what I want to do is to first calculate the revolutions per second. So it's taking the revolutions per minute, divide that by 60. Then to get the time per degree of rotation, we take 1 second, we divide that by 360. That's the amount of degrees in a single rotation, and we multiply that by the revolutions per second. Essentially, how many degrees of rotation do we have in 1 second? So that gives us 0.00119 seconds per degree. By that, then we can calculate, based on the length of time that the exhaust valve is open, we multiply the exhaust valve opening time by crank 150 by the seconds per degree. That gives us 0.0179 seconds. So what we know now is the exhaust valve opening time. For pulse tuning, the exhaust gas starts to leave as soon as it opens. When it reaches the expansion, it will then bounce back that pulse of negative pressure. We assume that the velocity that it's traveling is the same throughout that full distance that it's going to travel, both away from and back to. And we want that to return at a number of degrees before the exhaust valve closes, so that we can get the benefits of that negative pressure. So in this example, I just plot in 15 degrees before it closes. Okay, so now we know the degrees. Okay, so now we know the degrees of rotation before the exhaust valve closes that we want the pulse to return. We consider the velocity that the gas is flowing. So I've assumed the speed of sound. The speed of sound does change with temperature, however, so this is a little bit less than it would be. Okay, so in this example, we say we wanted the pulse to return to the engine 15 degrees before closing. So what we want to consider is the total time for pulse to travel. So we know the total opening is 150 degrees. We subtract the 15 degrees, that's 135 degrees, and we multiply that by the seconds per degree. That gives us how long the exhaust gas is traveling for, both away from and back to the exhaust port. We assume an exhaust gas flow velocity. So in this case, I've just used the speed of sound. The speed of sound does change with temperature, so this is a little bit of it's lower than it should be. Total time to reach the first expansion can be got by dividing the total time for the pulse to travel, based on what we just mentioned a moment ago. We divide that by 2 because it has to travel half the length before the pulse then returns. So that gives us 0.008 seconds. If we multiply this by the exhaust gas flow velocity, we'll get a distance, and that distance is where our first expansion should be. You'll notice that the distance here is longer than your motorcycle, so we're really not going to tune for this kind of condition. Bear in mind, this is basically our idle. Based on our conditions here, we can adjust this and we'll end up getting a shorter length, something more achievable. So let's say you want to tune for 6,000 RPM, like a nice cruising speed. Now we got the expansion distance should be about 0.64 meters from the port. Let's say our gas speeds are a bit faster, let's say 400 meters per second. So it's about 0.75. Because it's faster, it can travel further, but we can also adjust when it returns back to the port, when the pulse returns. So essentially this is kind of how we would determine where the expansion should be. And then there is also the size of the diameter. The diameter, as I mentioned, is going to affect the flow velocity as well as the friction and the back pressure. We'll come on to that perhaps in part 2. And at part 2, once I've validated all of these calculations, I'll also share this sheet. Now, if you're still watching at this point, I just want to say thank you very much. I'm very surprised, but very grateful. So here's a few custom paint jobs that I came across during the motorcycle show. So this is the Honda CB1000F. To be honest, it's a pretty basic design, but the next one is what's most impressive. This is the Suzuki GSX-8R. And this is a special paint job for the Street Fighter 6 video game. I think the color coordination for the brake calipers, the details on the fairing, the bolts, everything being this light blue is a really nice touch.